Good. Well, we got a little better attendance today, which is good. I feel terrible because the makeup lecture didn't post, and I have no idea why. I've just been told this. We're trying to look into it. I've talked to the EPE people, but it's kind of like these things where, you bought a car, and the car manufacturer is saying it's the fault of the engine manufacturer, and the engine manufacturer is saying it's the fault of the carburetor manufacturer. The carburetor's fault is the manufacturer saying, I can't understand what you're asking. And yeah, so I'll keep trying to track it down and figure out what happened, but the video didn't post for some reason. Okay, so we're still doing the EM algorithm. Maybe I have to do a little bit of review. So for people who haven't seen the lecture, for people who haven't seen the lecture, last time I mostly talked about section 8.3 of which is the theoretical techniques for the EM algorithm. Okay, and I'll do a quick summary since the lecture didn't post. By the way, the attendance wasn't so great on Monday at 5:30 either, guys. Okay, so okay. Now, so the upshot was this. Hold on. What am I doing there? Yeah. Okay, so we covered this section here, and the upshot of it, I'll just give you the quick summary. This is like when you watch a serial TV show, and then they have like a 30-second recap of the last 6 months of Downton Abbey. Has anybody ever watched Downton Abbey? No? Okay. So you have a log of P of Y given theta, right? And that's the log likelihood. You're supposed to maximize with respect to theta in order to estimate the distribution, okay? And, hold on. Oh, God. Oh, I see. Okay. Forever learning. Okay, and you can decompose this into two functions. Q of theta prime, plus H of theta prime. Okay? And you say, well, what's theta prime? The theta prime is anything you want it to be, but what it's going to be is we're going to iterate, okay? And for each new update, we're going to, theta prime is going to be the old value of the parameter, and theta will be the new value. So the EM algorithm is actually this. This is the EM algorithm. It's just repeat. Well, I guess there are 4, k equals 1 to whatever. Okay, and then you just do theta k plus 1 equals the R max over theta of Q of theta prime. Okay? So that's the EM algorithm, right? And you say, okay, so it turns out Q is an approximation of the log likelihood, and every time, and it's an approximation. You can think of it, okay, what I'm about to say is false, okay? But it's a good way to think of it. It's like a Taylor series approximation to the log likelihood about the point theta prime. So Q is an approximation, but it's an approximation that lower bounds the true log likelihood, and it's equal at that current point. Okay? That's not exactly true, because what happens is that there's an offset constant, okay? So actually, what you can do here is you can say, well, I'll define h of theta prime, okay, to be equal to this h of theta prime minus h of theta prime, okay? You can define this, and you can define q, lowercase q of theta prime to be equal to q of theta prime plus h of theta prime. So if you do that, then it's a little more intuitive, actually, if you do it this way. The answer comes out the same, but it's a little more intuitive. The little q and h are a little more intuitive in terms of explaining it, but the big q and h are the way you actually define the quantities, and when you do the calculations, these are easier to use. So the reason you say, well, why not just define it with the little h and q? Well, because if I define it with the little h and q, it makes the calculation really complicated, and it also makes the derivation really complicated. But the little h and q makes the interpretation easier, okay? So it's just a constant, right? Because for h prime, this is h prime of h prime, this is the constant. But in this case, what happens is that if you have like the log likelihood, you're doing maximization, right? So this is the log likelihood. This is log of p of y given theta, right? And this is your current operating point, theta prime, right? And then what will happen is that you have a function which lower bound, and it's tangent and is equal at that particular point, so it's also tangent. And that function here is this lower q of theta prime. And of course, the lower bounding approximation is going to be different for each position. If I move theta prime, it's a different function. The q here has to be a function of both theta and theta prime. But we're only really varying with theta prime with theta. Theta prime is sort of fixed in each iteration, okay? The notation of the EM is a little complicated. But that's actually a very good thing. And it is because if you learn the EM algorithm and really understand it, then you can go get a job, okay? If you can go to your employer, and your employer can say, you know, we have to do this thing with this EM algorithm, and you can say, I know how to do that. And everybody else will be confused because they didn't read these notes carefully, okay? So what is actually an obstacle can be an advantage, okay? Good, okay? So I just wanted to provide a little bit of inspiration, okay? So this q is a lower bounding function. It's very intuitive. If you maximize the little q, okay, you'll get an increase in the actual log likelihood. So every iteration of this EM algorithm will increase the log likelihood, right? It makes perfect sense. And with this definition, then h of theta prime equals 0. And if you draw the h function, and so this is position theta prime, the h function will have its minimum, so this is theta, and the h function will have its minimum, this is h of theta prime. The h function will have its minimum at theta prime, and it'll be a strictly positive function which is equal to 0 at theta prime. So this is the little h function. Okay, so in the notes, I'm kind of covering things a little bit non-linearly here, which is good, because if I just cover them exactly the same way the notes were, then what would be the point? Just read the notes. Here's the, I know it's here somewhere. Hang on, just a moment. This is blah, 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 blah. Converges. Oh, yeah. They actually gave me these equations numbers, but this is actually section 8.6. So if you look at section 8.6, it has this definition of the little h and the little q, okay? It's just shifted versions of the big H and the big Q, okay? Now, why is this true? Well, it's true because I proved it, okay? And the proofs are based on Jensen's inequality, and that's what's in section 8.3. You can go through section 8.3 and go through every line of every proof and make sure that you're completely convinced that every step is true, right? And then if you believe in mathematics, then it must be correct, right? So, if you believe in mathematics and logic, and you don't think there's something wrong, you're not really suspicious about this whole thing, then you have to accept the fact that this is true, right? So, all right. So, does that make sense? Now, okay. So now that has some consequences. Oh, there's a few consequences, which is that the gradient with respect to theta of the log likelihood evaluated at theta equals theta prime is equal to the gradient of the Q function evaluated at theta equals theta prime. So that's maybe a complicated formula, but all I'm really saying there is the derivative of the two functions has to be equal at that point. All right? And what else am I saying? I'm also saying that well, the other thing I said is that the minimum of the h function, this little h function, occurs at theta prime. Okay. Now, so what does all this mean? Okay, so I try to oscillate back and forth between some theoretical ideas and some applications of them so you can see how it fits together. So the application here is clustering. When we talk about clustering, the clustering is not the only application in EM algorithm. There are many applications in EM algorithm, but it's sort of the most canonical. I think it's easiest to understand. It's the most intuitive. So, so you have a bunch of random variables. So you have basically, xn, and then for each xn, you have a yn, right? And that arrow, which I'm going to start using more, is used to show conditional dependency. So we have y of n given x of n is going to be a Gaussian distribution. It doesn't have to be Gaussian, but let's pick Gaussian, okay? It's going to be a Gaussian distribution, so it's normal, and the mean of Gaussian is going to be mu sub xn, because xn is a discrete value. So xn is going to be, say, 0 or 1, I think is the case we're going to do first. We'll do, let's say, so xn, the probability of xn equals m. I'm going to use the same notation. It's going to be equal to pi m. Okay. So this is a parameter to the distribution, and also say the xn are IID. Right, they're all the same distribution. So they're basically, what is it, Bernoulli random variables. So like you had a bunch of different colored ping pong balls, you threw them in a bucket, you close your eyes and you pull one out, okay? So the probability, and with replacement, okay? If it was not with replacement, then they wouldn't be IID. So you put them back in, you mix them up. It's like a state lottery, only you don't cheat. Okay? But you mix them up, and you grab in there, and you pull the ball out. Okay? And now the conditional distribution of y given x, then each x is a discrete value. It's a value between 1 and n. So each xn is going to fall into the set through m minus 1. That's the way we're going to do it. So x is a discrete value, and it indexes mu. So then this is going to be sigma xn squared, right? Now, so that's a normal distribution. So it's conditional. So are the x's normally are the yn distributed as normal random variables? Gaussian random variables? No. Thank you for saying no. I'm very impressed. Okay, why? Because they're conditionally Gaussian, but they're not Gaussian. There's a mixture of Gaussian. So what's the distribution of the y going to look like? This is sort of y. If I look like the distribution of y, let's say this is p of y, right? It's going to actually be the sum from m equals 0 to m minus 1 of the probability of yn given xn times pi n, right? So it's going to kind of look like this. If there were like 3 classes, right? And then you're going to take this lumpy thing, and you're going to try to estimate the mean and variance of each of those things. It's not an unreasonable thing to try to do, because a human being could look at this and say, well, okay, I think the mean of this is about here, that's about here, this is about here, right? And then you could sort of fit this and try to figure out how wide these were, too, and that would give you the standard deviation. But what's the systematic way of doing that? Well, to do that, we're going to use the EM algorithm. So this is called a Gaussian mixture. So P of y, this is called a Gaussian mixture, right? And okay, so now what are we going to do? Well, now if we had x and y, we could observe both. We could collect the following statistics. We could do this. We could say, okay. So this part gets messy. And you know what I'm going to do? This is kind of cheating, but at this point I'm going to just walk through the notes, because the equations are so messy that for me to reproduce them is just going to take a lot of time and not add a whole lot. So I'm going to just walk through them, and then it's going to turn out that okay. So the reason we're doing this is let me I need to make a point here. Okay, so with the EM algorithm, we now reached a certain point where we're going to actually do the calculation. And this is how it works. You have to do the calculations by hand once, so that you can learn that it's horrible. Okay? And I'm actually going to do it only for a very simple case. And the answer, we're going to go through these calculations, and it's going to come out, it's kind of a messy thing, and I'm going to just walk through it in the paper, but you need to go through every line very carefully. And you'll see that it's a messy calculation. So the point, and in the end we'll get an answer, and the answer will look very intuitive, hopefully. So the point of this is for you to learn that you don't want to do it this way, okay? It's as if you had to dig a hole, okay, in your backyard for a tree. And you said, first you got out the shovel, and you dug the hole, and it took you like a week, okay? And then you said, well, I really don't want to ever have to do that again. So instead, the next time you go out and rent a backhoe, and then you just dig the hole, and it's really easy, okay? So the point of this is we're going to learn that this is a hard calculation to do, but there's obviously something going on here that makes it, the answer, simple in the end. So what we're going to then do is hopefully that will be enough motivation for you that then what we're going to do is go back and learn a bunch of other stuff that is going to make it much easier. We're basically going to go to the rental store and rent the backhoe, okay? And the backhoe is going to be some powerful theorems, okay? It's going to be like one theorem is, we're going to learn about sufficient statistics and complete sufficiency. Oh, well, we don't actually learn about complete sufficiency. We'll learn about natural sufficient statistics of exponential distributions. And then we'll find out that there's a general form to the answer. And once you learn that general form, you can always do the calculations of these EM updates very easily. You basically just write the answer down, okay? So it's really also handy if you can do party tricks with it. So if you're at a party and somebody asks you, what's the EM update for an exponential distribution that's binomially sampled, okay? You can say, well, it obviously has this form, okay? And you can impress all your friends, okay? Okay, so the roadmap here is we're first going to do the calculation manually, and it's going to be ugly. And I'm going to just walk through it carefully. And then what we're going to do is we're going to actually derive a bunch of stuff, which, by the way, is also useful for other things, so you should try to pay attention, okay? And then once we derive this other stuff, we will use the power tools that we developed to solve the EM algorithm calculations really simply, okay? So that's kind of the roadmap. Okay. So now I'm going to go through the equations here. Okay, so this is just the joint distribution of y and x. So if we had both y and x, this would be the joint distribution. The problem is we're missing x. So we can sum, this is actually sort of a clever way. Pointing to the first equation in section 8.4, which is the joint distribution of y and x. Then the next equation at the top of page 165 is just expresses that as a sum where we have a delta function for each x. And this is true. It's not entirely clear why we run write it this way, but this is the log distribution. So when I take the log, I can take this product turns into a sum, and then I can sum over all the classes, but I only keep the k when x is equal to n. This just looks like a very complicated way of writing something simple. And you say, well, why would I bother to do that? Just hold on there, okay? So this is the log joint distribution. This is the log joint distribution of the entire sequence. The previous thing was the log distribution of each individual sample, okay? So this is the whole sequence, and I sum that from n equals 1 to n, because I want to take, they're independent, right? For each x and each y, the pair x, y are independent. They're not independent of each other, okay? They're independent for the pairs of x, the xy pairs represent single random random vectors. They're independent from different values of n, okay? So I can just take the sum of the logs of the probabilities to get the log of the probability of the sequence, because I take the product of the probability density for each pair, right? Okay, so I write this thing down. So now the Q function is defined as the expected value of the log of P of y x given theta. Okay, so let me back up here a little bit and make a point, which is this. So remember, the whole concept of the EM algorithm is that we would like to have had the log of P of yx given theta. We'd like to maximize that with respect to theta. That would give our estimate of theta. But the problem is we don't have x. So since we don't have x, what do? We take the expected value over the random variable x conditioned on what? Well, conditioned on y, but also conditioned on some initial assumed value of theta. So we start with some value of theta, we use that to compute the conditional distribution of x, and then we take the expectation of the log likelihood to get rid of x in the log likelihood. So this is the definition of the Q function. See, the EM algorithm, you have to understand it on lots of different levels in order to understand the whole thing. One thing you have to understand is that optimizing the Q function optimizes the log likelihood. So that's what we've talked about so far. The other thing you have to understand is that the definition of the Q function is that you pretend you had all the data, and then you take the expectation over x in the log likelihood expression. That's what the Q function is. So you don't really have to memorize the Q function. You could write it down. You could just say, well, it's got to be, it's the log, I would like to have the joint log likelihood of the combination of x and y, but unfortunately I'm missing x. So I'll take the expectation over x, and when I do that, well, I have to condition on something, so I condition on y, the data, and I condition on an assumed initial value of the parameter. And then I'm going to repeat this every time I update to do a step of the EM algorithm. Does this make sense?
I mean, we don't have the parameter too, so what sort of initial value are we talking about?
We can start with anything.
I will convert.
That's the next section, or 2 sections away. 8.6, conversion. It will converge in the following sense. Every time I update, every time I do an EM step, the log likelihood will increase, right? So I'll get a monotone increasing sequence of log likelihoods. If they're upper bounded, they'll converge to something. Okay? Now, that's really sidestepping your question. You know? This is like, you know, because really your question is a hard question to answer. Will the values of the theta, sequence of betas converge to the maximum likelihood estimate? It's a little complicated. We'll talk about it later. But in any case, every time you update theta, you'll get a larger value than log likelihood, which is a good thing when you're trying to do maximum likelihood estimation, right? The EM algorithm is an optimization algorithm, is what it is. It's a method of optimization using subfunctional, or substitute functional, or surrogate functional, maximization, majorization techniques that we talked about in the last chapter. That's why I made you suffer through that, because once you understood that, then this is a lot easier to understand, okay? So now, okay, so you got this in your head? Okay, so now, what's the specific form of, this is fine in general, in abstract, but what's it specifically going to be for an actual Gaussian mixture distribution? So let's actually plug and away, calculate this joint distribution, and take its expectation, and we'll actually get an expression for Q, okay? Is everybody on board with this? You see where we're going? Yeah. Now, so we're back on page 165, section 8.4, and we have an expression now for the log of P of y x given theta, and it's got a sum over n and a sum over n. So we sum over all the points in time, and we sum over all the classes for each point in time. And this will be the joint distribution, because we just plug this expression in sums over n, basically, right? So now, in order to compute the Q function, we have to take the expectation of that thing, right? So the Q function, Q of theta, comma, or semicolon theta prime, is going to be the expectation of this log of the joint probability of y and x, where we take an expected value over x given y and theta prime, okay? So we just plug this expression into the expectation, right? Oh, into the expectation here, right? So that's what this is. I just plug that in here, right? Now, this is a sum, so I can take the expectation inside the sum. And this expression involving the logs doesn't depend on x. The only thing that's a random variable here is this. That's the only random variable. So basically I can take that all the way inside to this part here. So, well, what's the expectation of delta of xn minus n? Let me write that out separately. What's the expected value of delta of xn minus n? What's that equal to? So the delta is 1 when they're equal, right? If you take the expected value of a delta function, by the way, what's the expected value of the delta function of an event A? So this is called an indicator function. It's 1 if omega is in A, and 0 if omega is not in A. Well, by the way, the omega here is like the probability space or a random variable. So if you have a function which is equal to 1 when the event, okay, so let's say, I'll make it a little more concrete. So delta A is equal to, so like A is the event that flipping the coin comes up heads, okay? So delta is equal to 1 when the coin comes up heads, and it's equal to 0 if the coin doesn't come up heads. Then what's the expected value of delta? Huh? It's going to be equal to the probability of the event A, right?
So wouldn't it be, so let's say you have like, wouldn't it be expected value of A over like the probability space? Oh shoot. Sorry, keep going.
No. You're asking a very good question.
Like the area, the area of the probability space. So I guess what I'm saying is, let's say you're on like a two-dimensional probability space.
What's the expected value of 1?
1, right?
Okay? But
Yeah.
come on, the probability measure has the property. It's the integral, right?
Yeah.
Of 1 times dp of omega, but the probability measure has the property that it integrates to 1. Has a total measure of 1. So it's not just any measure. Like if you took Lebesgue measure on a real line, this would be infinity, right?
Yeah.
Okay? So you kind of have this underlying thing that the overall probability measure integrates to 1, right?
So, like for example, let's say that the value 1 was defined on the origin, and your probability space was two-dimensional from like -5 to 5. Into like two-dimensional.
Uniformly distributed or something?
Yeah, uniformly distributed. Cartesian space, -5 to 5, 2 dimensions. Then.
But does it have to be 2 dimensions?
Or it'd be whatever. It doesn't matter. Who cares? But then wouldn't the expectation of the delta function in this case, you would need to shift it. Wouldn't it be the value like divided by the area of the probability?
Well, actually, in this case, so if we use Lebesgue measure, right? So you have a random variable x, right?
Yeah.
And so we have this function f of x is equal to 1 if x equals 0 and equals 0 if x is not equal to 0, right? Okay. So and x is uniformly distributed. So the probability distribution of x is 1/10 for x with magnitude less than 5, right?
Yeah.
Okay. So in this case, the expected value of f of x is equal to 1.
F of x is going to be 1 times
0, right? Because this is the probability that you're going to, the dart's going to hit bullseye.
Yeah, okay.
Okay? So the other way of looking at this is the integral of this function is also 0.
Yeah.
If you do Lebesgue integration, you find out that the integral function like this is 0.
Okay.
So the indicator function concept is that if you have, so if delta of x, right, so if you have a function, okay, so if you have a function and it's equal to 1 if x is in A, and it's equal to 0 if x is not in A, right? Then what you're going to end up having is you'll have the integral of delta A of x times, using sort of simple notation, times p of x dx, right?
Okay.
So that's going to be equal to the integral over a of p of x dx, right? And that's going to be equal to the probability that x is in a.
Okay.
So my point here is that you can express probabilities as expectations. This is actually a very general property that I kind of alluded to at the beginning of the semester. And I said that you can build probability with expectation. You don't need to use density. Okay? So the probability of an event A is just an expectation of the indicator function. Okay? I can put an X here. It'll make you feel better than putting an omega there. Okay? Okay? Right? It's like, once you actually see it, it's so obvious that you can't remember why it wasn't, it ever seemed unclear. Okay? But before that, it seemed miraculously hard to understand. Okay? So, it's kind of interesting. After years of teaching this, I know what people have trouble understanding, but it's hard for me to remember why. Because I learned it. When I first learned it, of course, I didn't understand it. It didn't make it. I had the same conceptual issue. But now it's like a dictionary that I keep track of. That I just know. Okay, this is hard to understand. This is hard to understand. But it's hard for me to remember why. So basically, the expected value of this delta function is going to be 1. So the expected value of delta of xn equals xn minus n, that's going to be equal to 1.
Probability.
That's just the probability that xn equals n. It's just a fancy way of writing the probability. And if the conditional expectation of delta xn minus n, given, I don't know, whatever, but I'll say y and y. Oh, actually, I only need yn equals yn, and zeta prime. What's that going to be? So that's going to just be the conditional probability of xn equals n, given yn equals little y and zeta prime. Okay? So that's what this is. So now we have, this is the Q function. So there's the Q function. The Q function is, what you've done is each of these terms in here looks like the log probability distribution for the nth random variable y, right? Y to n. Okay? But it's computed with a conditional expectation over the unknown value of x. Because you didn't know what n was, so you took an expected value over the axis. Now you say, well, how do I calculate this? Well, I can actually calculate this conditional expectation. This is like the posterior distribution in Bayesian estimation. You could just use the standard Bayes rule to do it. You know what the numerator of this expression at the bottom of page 155 is the joint distribution of y and x, right? So then you divide the joint distribution of y and x by the sum of that joint distribution over x, basically n in this equation, and this is Bayes rule. So this looks kind of a mess, but it's easy to calculate. You just and the thing on the bottom is just the normalizing sum. It's just to ensure that f of n sums to 1 when you sum it over n. Because it's got to be a probability distribution, so it's got to sum to 1. If it didn't sum to 1, it wouldn't be a valid probability distribution, right? So with that, then, you have, now what happens is the next part of it, it's like so horrible that I skipped it, okay? Because I couldn't bear it. You wouldn't bear it. You could go through this, it'd be like a mess. But basically, now once you have this Q function, you can maximize the Q function with respect to theta. So, now, we've done, I hope you did the homework. Because in the homework you were supposed to have computed the maximum likely estimate of the mean and standard deviation for Gaussian random variables, and you were supposed to have calculated the maximum likely estimate of the like a Bernoulli random variable, or, right? This is the same thing. It's just a little bit messier because you have the sum over m. But it's the same thing, okay? So you could just apply the same machinery, turn the crank exactly the same way as you did for the homeworks in chapter 2, which is why I made you do those, okay? And if you do, these are the answers you get, right here. Equations 8.13 through 8.16. And they're very intuitive. So the expected value for, okay, so this n hat m is an estimate for the number of samples that come from class m, okay? So it tells you, essentially what you're doing, and I'm going to talk about this in a moment, if you're sorting your samples, remember, to start off with you had a bunch of samples, right? And each sample were drawn from a different distribution. What am I doing with this? Let me do this under here. Oh, yeah. You started off with a bunch of samples that were independent. Each one, X came from a different, was randomly selected from a bucket of balls, that, like ping pong balls, of different colors, okay? So you pick the color, and then based on that color, you had a Gaussian random variable here, right? So then the question is, for each sample, which class did it come from? Well, you don't know for sure, but you can sort of guess that it fell in each class with some probability. So what you do now is you say, well, what's the total number of ping pong balls that were in class M? Well, you sum over for each sample the probability that it was in class M. This is the expected number of balls in ping pong balls in class M, okay? This is now the probability, so if you take that number and you normalize it by the sum has got to be n because there were n samples, right? So since there were n samples, every ball has to belong in the one sample. So if I sum this n, I can show that this n half of n will have to sum to n. So if I normalize it, I get an estimate. This is the maximum likely estimate of the probability of the distribution for the distribution of the colors of the ping pong ball. Okay. Now it's really the EM update because it was based upon this assumed parameter theta k, and then mu here is the weighted expected value, and sigma e squared here is the weighted variance. So these are just horribly intuitive. Okay. I mean, basically, you take your samples, you guess what the mean and variance of each class is. You use that to compute the posterior probability that each ball fell into each class. Then you take instead of just taking the average for each class, you take the weighted average, where the weight is the probability that the ball fell into that class. Okay? It's just like what you would do if you were just hacking around, making up something that made sense. Except where it actually falls out of this theory. It falls out of the theory of this, that you know this Q function has this property that it's a substitute function for the actual log likelihood, and each update of the Q function will produce a better estimate of the maximum likelihood estimate, okay? And each one corresponds to this interpretation. Now, if you look at the next section, 8.5, I break it down into a more algorithmic format, which I think is easier, corresponds more to what you would write in a computer program. And by the way, you have a lab where you have to do this. So you should definitely go and read these very carefully so you understand it. When you write the lab, you'll save yourself a lot of time. Because if you try to write the lab without understanding what you're doing, you know how that goes. You'll spend like 6 months debugging your program, right? So here the E step, first you calculate P sub nn. P sub nn is the probability that the nth sample came from class M. it's the conditional probability that that sample came from that class, okay? And you can calculate it, that's just this posterior probability that you calculated, right? So you update the piece of MN, this is a matrix. The picture is like this. If you look at figure 8.3, I spent so much time drawing all these little figures. I hope you appreciate it. So, in figure 8.3, what happens here is that for each sample, it's going to belong, it belongs really only to one of the classes, but you don't know which one. It's the probability, it's never going to have a probability of 0 of belonging to any of the classes because the Gaussian distribution has infinite tails. So there's always a small probability that any of these distributions could have generated any sample. But sometimes it gets exceedingly small. So what happens is that you'll look at Y and there'll be a probability it came from each of the classes. And the PNN tells you the probability that the nth sample came from the nth class. So every sample is partitioned among the classes in some proportion. But in practice, some of these samples, some of these proportions could be like 10 to the minus 30, okay? So it's like really a small probability. So then, once you have these partitions among the different classes, then what you do is you do the M step. In the M step, you take all the samples that fall into a single cluster, and for that cluster, you estimate the mean, the variance, and the number of samples. That's the M update. So the M update, you sum for P and M over N, and that gives you the expected number of samples in each of the classes. And then normalizing that, you get the probability for each class occurring. Then, if you take the weighted average of the observations associated with that class and normalize it by the number of samples in the class, then you're going to get the mean for that class. And then the standard deviation. But the thing is this, once you update the mean and standard deviation, now you have to go back, because now your estimate, your posterior probability has changed. Your parameters are new. So basically, I don't know how many people have ever done the K-means algorithm. This is very much like the K-means algorithm. This is just a more sophisticated version of the K-means algorithm. Basically, you take the samples, you put them into clusters. Then for each cluster, you re-estimate parameters. Then based upon those parameters, you re-partition them into clusters. And you keep going back and forth, clustering and re-estimating parameters. It's clustering, partitioning, and re-estimation of parameters. Partition, re-estimation of parameters, until you converge. And you know you have to converge, because every time you're doing this update, you know the Q function is getting bigger. And since the Q function is getting bigger, the log likelihood is getting bigger. So if the log likelihood, if the maximum likelihood estimate exists for the log likelihood, then you've got to converge to something, because eventually the log likelihood has to be bounded above, right? So in other words, now in fact, I'm lying to you slightly. Well, I'm lying to you a lot, actually. I'm misleading you on purpose, because there are some assumptions I'm making here which are false. In fact, the maximum likelihood estimator may not exist as a problem, and it generally doesn't, okay, for technical reasons that I hate to have to explain to you, but you're going to learn about it sooner or later, so it may as well be now. That maximum likelihood estimation for Gaussian mixtures is sort of not well posed, because let's say you have a bunch of samples, okay, and you want to estimate the mean and variance, okay? Well, you could take just one of these samples and you could make it its own class, and you could set the variance to 0. And then you get a really highly peaked distribution just around that one sample, okay? But the log likelihood will go to infinity. But intuitively, you look at this and you say, well, come on, that's silly. I mean, the one sample isn't just its own class. I mean, I guess that's possible, but it's highly unlikely, right? So, in practice, you get rid of those. You bound yourself away from those. Okay, I'm running out of time. Okay, yes. So now we got the EM algorithm. You got the interpretation of the Gaussian mixture. Go and read this very carefully so you understand it, because now I'm going to be depending upon the idea that you understand it. We're going to use this for hidden Markov models, If you don't understand, you'll be confused. Read the notes very carefully, okay? I'll see you next time. All right, thanks. Hi, Alex?